So here we're just going to get a few more examples of finding that equation of the tangent line given a point and given a function. And what we're working with here is that first derivative is going to give us the slope of that tangent line, which we calculate by taking that limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so let's go through these together. So 2x squared plus 1 going through the coordinate 1, 3. Again, we want the equation of the tangent line, so we're fitting this y equals mx plus b form. And like I showed in that last video, we could check our answers by then graphing in a calculator at the end to make sure that it looks like our function along with the tangent line. Okay, so we're going to look at our first derivative, and our x value from our coordinate is a 1. So we want to evaluate the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And again, it's your choice of if you want to do the calculation all in one or separate it up. I'm going to go ahead and just do this all together, but either way works. So limit as h approaches 0, so we're doing 2 times 1 plus h squared plus 1. So there's the f of 1 plus h, and then we're going to be subtracting and just plugging in 1, which this should always simplify just to a single value, but just to show my work, 2 times 1 squared plus 1, all over h. So I want to simplify that first set of parentheses and second set of parentheses and evaluate their difference. So the limit as h approaches 0, so we're going to have 2 times, and if I FOIL out the 1 plus h squared, that'll be 1 plus 2h plus h squared plus 1. And then we are subtracting 2 plus 1, which is 3, all over h. Okay. Limit as h approaches 0, and something that's important is you should be keeping that limit notation all the way until we end up plugging in h equals 0. So it needs to stay there until we make that substitution of h equals 0. So we're going to distribute the 2, so 2 plus 4h plus 2h squared plus 1 minus 3 all over h. So 2 plus 1 is 3, minus 3 turns into a 0. So we have 2h squared plus 4h over h. And h should cancel out so that we have 2h plus 4. And now we can plug in h equals 0. So we lose our limit notation because we're making that substitution, which we're getting out a value of 4. So that's telling me that for our equation of a tangent line, we're going to have y equals 4x plus b. And to find b, we're going to plug in our coordinate 1, 3. So 3 equals 4 times 1 plus b. Subtract 4 from both sides to get a negative 1. So our equation of the tangent line is going to be a 4x minus 1. And then we could go ahead and graph that to double check. All right, another scenario here. We're going to take the first derivative of our function at x equals 0. Ooh, this is going to be nice because with zeros, a lot of stuff just cancels out. So the limit as h approaches 0 of 2 times 0 plus 8. Ooh, I'm going to write out the full notation since we're getting started with these. So I'm looking at f of 0 plus h minus f of 0 all over h. And you know what? Something I did here, which you could have skipped a step where I did finding f of 1. We actually are given f of 1 here because they're giving us that y coordinate. I could have made a direct substitution there. It's good practice to plug in, especially if they only tell you that x equals 1, because then you'll have to calculate it. So the y coordinate won't always be given to you, but you can always find it. So limit as h approaches 0 So we're looking at 2 times 0 plus h, which is really just h. So really what I'm doing here is just looking at if it's 0 plus h, really just evaluating f of h. So what we can do is just make the substitution of h equals x. So this will be 2h squared plus 2h plus 1 minus f of 0, which they're giving us the y coordinate, which is a positive 1, all over h. So the constants should cancel out to a 0, then we could divide out a h, which would leave us with a 2h plus 2, plug in h equals 0, and we'll end up with a positive 2. So we're getting y equals 2x plus b, and actually they're giving us our y-intercept as a positive 1, so we know that b is a plus 1. So we're getting a 2x plus 1 out for our equation of the tangent line at 0, 1. All right, let's look at some rational functions here and some algebra review of how to deal with those. Okay, so f prime of 1, we're evaluating that limit as h approaches 0 of f of 1 plus h minus f of 1 all over h, which will be the limit as h approaches 0 of 1 over 1 plus h minus 1 over 1, which is 1, all over h. And let's get a refresher of what we do with these complex fractions. So we want to multiply everything, or rather, we want to multiply the numerator and denominator by the least common denominator, which what I'm looking for with that is just that 1 plus h. So what I'm going to do is multiply the numerator by 1 plus h, multiply the denominator by 1 plus h. And what that'll do is that 1 plus h is going to distribute in. So in simplifying, what we'll have, I'm going to write this all out for us just to get a really good review. So we'd have 1 over 1 plus h, and that's being multiplied by 1 plus h. We have a minus 1, and that's being multiplied by a 1 plus h, and then dividing by h, which is also being multiplied by a 1 plus h. And when we do this, our complex fraction should cancel out. It's like that 1 plus h is going to cancel out and just leave us with a 1. So we're going to have our limit as h approaches 0 of, that cancels out to be a 1, minus, and we're going to distribute that negative 1 in. So we'll have a negative 1 minus h over, and then I'm going to leave the denominator factored out because we're looking for some cancellation. We're going to work with this until we can plug in h equals 0 and get something that's defined. So this will simplify to a negative h over h times 1 plus h, and because I left it factored out, I can see this cancellation of an h, which will leave a 1 up in that numerator. And now I'm at a spot where I can plug in h equals 0. So I'm going to have negative 1 divided by 1 plus h, but we'll plug it in as 1 plus 0. So negative 1 over 1 is a negative 1. So our equation of the tangent line will have a negative x plus b, and then plug in our coordinate 1, 1 to solve for b, which will give us a 2. So y equals negative x plus 2. Let's get even a little more complicated here for some good review of our rational functions and how to deal with it with our limit definition of our derivative. All right, so we're looking at f prime of 0. So we're evaluating that limit as h approaches 0 of f of 0 plus h, which is really just f of h, minus f of 0 all over h. So we want to be careful because we have this negative symbol out front. So we're going to have a negative 1 over h plus 2 minus f of 0 is a negative 1/2. So we'll have minus a negative 1/2, which will be a plus 1/2. Let's go ahead and just simplify that with a plus 1/2 all over h. Okay, so my least common denominator, we're going to have a factor of 2. We're also going to have a factor of h plus 2. So what I'm going to do is multiply across the numerator. So we're going to have a 2 times h plus 2 there, and a 2 times h plus 2 there, and in the denominator, 2 times h plus 2 multiplying there as well. And we should get some nice cancellations here. So h plus 2's cancel, 2's cancel, so that we're left with negative 1 times 2, so negative 2, plus a 1 times h plus 2, all over 2h times h plus 2. Again, I'm going to leave that factored because we should be getting some cancellations. So with this, we're left with just h in the numerator over 2h times h plus 2. We'll get the cancellation of the h's to leave us with the 1 in the numerator, and then we can plug in 0. So this will be 1 over 2 times 0 plus 2, which is a 1/4. And there's our slope of the tangent line. And then going to plug in to find our intercept, we actually are just given the intercept because we're working with x equals 0. So this will be a minus 1/2 for our intercept. And that'll do it. So this is how we'll be finding our derivative right now using that limit definition and evaluating, and then we could go as far as finding the equation of the tangent line. Just know that sometimes they'll only ask for that first derivative or just the slope of the tangent line, but I like these examples because it kind of goes through the longer process, but you can stop this earlier, like just ending with that 1/4 as the answer. But when they're asking for the equation of the tangent line, you want to make sure you're ending with a y equals mx plus b form.